Hello students, welcome back. The next topic is roots of unity. Please note that this entire subsection is de-emphasized in gray. That means it's an optional section. This entire video is an optional video. The reason? I think not everybody here is sufficiently comfortable with complex numbers. That's reason number one. The second reason is not everybody here is going to take abstract algebra 2. But if you have sufficient background in complex numbers and you're curious about this, or if you are taking abstract algebra 2, then you have to go through with this because this is important in field theory and cyclotomic field and things like those. Okay, let's begin. Given positive integer m, the group of mth root of unity is defined like this. It's a little bit hard to read, so let me expand the font. Exponential of 2 pi k over m times I power, or equivalently, cosine of 2 pi k over m plus I sine of 2 pi k over m. The latter expression and the former expression are identical. The reason? Because of this. Exponential of I theta is equal to cosine of theta plus I sine of theta. Now, do you recognize this identity? We went through this in Calculus 2. Let's begin with the Taylor-Maclaurin series expansion of exponential function. And instead of x, let's put I theta in there. Now, what is I? I is an imaginary number. I to the second power is -1. So, I to the every even power is real, and every odd power is complex. We have I times something real. So let's separate this infinite sum into even terms and odd terms. So we have 2k power, even power, and 2k factorial, even factorial. Here, odd power and odd factorial. Now pay attention to I here. Again, pay attention to I. But also +1. So I to the second power, what is I to the second power? I to the second power is -1, and then that to the k power. So this I generates -1 to the k power. Do you see that? Now this time, I to the second power, and then to the k power is -1 to the k power. And then we have +1, another I, so we have this I. And then the rest, we have all the odd power here, and all the even power here, and even factorial, and odd factorial. Consequently, we have cosine and sine. And then we have I here, that comes from this. That proved this identity. Exponential of I theta is cosine of theta plus I sine of theta. So this expression here up there and that expression down there are identical. They're the same. Sometimes this expression is more convenient, sometimes the latter is. Let's look at some pictures, and in this case, the latter expression is going to be a little bit more useful. Basically, it's this. Real part is x-coordinate, imaginary part is y-coordinate. So basically we have x-coordinate cosine and y-coordinate sine. So cosine of theta comma y sine of theta, basically what we get a unit circle. A circle with radius 1 centered at the origin. And in this case, m value is 7. So we have 7 dots starting from 1 here when k is equal to 0. And then 2 pi over 7 rotation, another 2 pi over 7 rotation, another 2 pi over 7 rotation, and so on. Let's run it again. And this time m equals to 2. This program is randomized, so you can run it again with different m value. This time m is 5, m is 9. I think I made my point. So we get all these along a unit circle, and a special case k equals to 0, then we have a real number, otherwise all complex. Now, why are they called roots of unity? Well, that's because of this. Let's expand the font again. That thing to the m power, well, let's apply the exponent rule. Multiply by power, and that'll kill off this denominator, so you get e to the 2 pi k I. So we get an integer multiple of 2 pi. So if you use the second expression here, cosine of theta plus I sine of theta, angle theta is integer multiple of 2 pi. So cosine of 1 and sine is 0, so in the end we get 1. So this thing to the m power is 1. In other words, this thing here is the mth root of 1, the mth root of unity. In a special case, we are restricting ourselves to real number system. In that case, this is just 1. But for complex numbers, they are m minus 1 more. When k is 0, yes, a real number. Otherwise, 1 through m minus 1, we have complex numbers. Now, please note that this UM forms a multiplicative group, and that group is abelian. Basically, we have this kind of multiplication, e to the 2 pi k over m times I times e to the 2 pi j over m times I. And then if we apply that exponent rule, we just add up the power. And when you add up the power, we have the same denominator. So basically, we're adding up the numerator. But then again, if you add up the numerator, what happens? This k plus j can be rewritten according to the division algorithm, some qm plus r, where q is a certain quotient. Consequently, this whole thing can be rewritten as so qm over m, and that one, plus 2 pi r over m, like that. And what is this? We have m over m, so we get just integer multiple of 2 pi. So we get exactly the same situation as this. This is 1. So we get 1 times exponential of 2 pi r over m times I, same as here. Sorry about the typo. So what do we end up with? We end up with a residue class, just a remainder, modulo m, and the remainder can be either 0, 1, 2, 3, all the way over to m minus 1. So what did he end up with? If you look at this multiplication in terms of exponential, we have addition on the powers, and furthermore, it's addition modulo m. Haven't you seen that before? Yes, you have. It's exactly the same as the residue class group Zm. So the group Um with complex multiplication is essentially the same as the additive group Zm the residue class group modulo M, something we studied before. So the conclusion is, you don't have to know anything about roots of unity because this is exactly the same as residue class groups. So why bother? Well, in abstract algebra 1, there's no reason, so many people don't cover it, and I'm covering it, yes, but I'm doing it only as an optional video. For example, most of my colleagues do not cover it. But if you need abstract algebra 2 and want to study field theory and Galois theory and some cyclotomic field and polynomials and those kind of things, yes, this is necessary. And that's another reason I did cover. Who knows, I may end up teaching abstract algebra 2. We'll see. In any case, for now, that's all done. So much for the optional video.